In the first 6 months of 2024, Mount St. Helens shook more than 350 times, a near constant tremor deep beneath its crater. And nobody felt a thing, not a single tourist standing at Johnston Ridge Observatory, not a single resident in the towns scattered across the Washington landscape. A silent, rolling earthquake swarm happening 4.6 miles underground. These were not the quakes of a crumbling fault line. They were the sound of a volcano waking up. The United States Geological Survey calls it magma recharge, a slow, steady injection of fresh molten rock into the shallow plumbing system that feeds the most active volcano in the contiguous United States. It is not an eruption, not an explosion, not yet. It is the mountain breathing in. And for decades, we've only ever seen what happens when it breathes out. If you remember the 1980 eruption, or if you've ever stood in its shadow, tell us one thing you remember in the comments below. The stories from that day are history, and we need to hear them. Now, a huge percentage of the people who watch our documentaries are not subscribed. When this mountain speaks again, you will want the scientific truth, not the viral panic. Hitting that subscribe button is free, and it ensures you get our analysis directly. It is the single most important way to support what we do. Let's begin. Before May 18th, 1980, Mount St. Helens was a picture of impossible symmetry, a near-perfect cone of snow and ice, so graceful that locals called it the Fujiyama of America. It stood at 9,677 feet, a quiet sentinel in the Cascade Range, dormant for over 100 years. Geologists knew it was a young, aggressive volcano. They knew its history was violent. But for generations, it had offered nothing but stillness. That stillness broke on March 20th, 1980, a magnitude 4. 2 earthquake shuddered through the mountain's core. It wasn't a singular event, it was a beginning. Over the next week, the seismic drumbeat intensified. Dozens, then hundreds of small quakes rattled the USGS instruments. By late March, steam and ash began venting from the summit, creating a new dark crater in the pristine snow. The mountain was clearing its throat. But something far more sinister was happening on its north face. The ground itself began to move. Pressurized by magma rising from deep within the earth, the northern flank of the volcano started to swell outwards at a terrifying rate, 5 feet per day. A grotesque, growing bulge, a geologic aneurysm that deformed the mountain's perfect cone into a threatening, unstable mass. Scientists called it a cryptodome, a bubble of molten rock trapped just beneath the surface, pushing the entire mountainside toward catastrophic failure. They knew it could not hold. The question was not if it would collapse. The question was when. Evacuation zones were drawn. Roads were closed. The governor of Washington declared a state of emergency. Still, the mountain held a fatal allure. Cabin owners defied orders to leave. Tourists snuck past roadblocks to get a closer look. Loggers worked in areas deemed a safe distance away. The bulge grew, relentless and silent. On the morning of Sunday, May 18th, 1980, the sky was a brilliant, cloudless blue. At an observation post 5 miles north of the summit, a 30-year-old USGS volcanologist named David A. Johnston was on watch. His job was to monitor the bulge, to take the measurements that might give some small warning of the inevitable. He was stationed at what was considered a relatively safe distance. He had a radio. He had his instruments. And he had a front row seat to the end of the world. At 8:32 in the morning, a magnitude 5.1 earthquake struck directly beneath the swelling north face. It was not the eruption itself. It was the trigger. The entire northern flank, the cryptodome, a cubic mile of rock and glacial ice, began to slide. It was the largest subaerial landslide in recorded history. 2.5 billion cubic meters of debris, enough to fill 1 million Olympic swimming pools, instantly let go. This massive failure of the mountainside acted like a cork being blown off a champagne bottle. The superheated, gas-charged magma that had been trapped inside was suddenly, violently depressurized. The result was not a vertical eruption. It was a lateral blast, a stone wind. A superheated cloud of ash, rock, and gas, moving at nearly the speed of sound, shot horizontally out of the volcano's collapsing flank. It incinerated everything in its path. Ancient forests were flattened in an instant. Trees 6 feet in diameter snapped like toothpicks. The temperature inside the cloud exceeded 600 degrees Fahrenheit. At his post 5 miles away, David Johnston saw it coming. He grabbed his radio. His voice was steady, professional, and final. Vancouver. Vancouver. This is it. Then the radio went silent. He was engulfed by the pyroclastic surge. His body was never found. The ridge where he made his last stand is now named in his honor. The blast didn't stop. It traveled for 23 miles, annihilating a 230 square mile fan-shaped area. The landslide swept into Spirit Lake, sending a wave 860 feet high crashing into the surrounding hills, stripping them of all soil and life. The vertical column of ash, which erupted moments after the lateral blast, punched 80,000 feet into the stratosphere in less than 15 minutes. Day turned to night across eastern Washington. Ash fell like snow in Idaho and Montana. Within 2 weeks, it had circled the globe. The scale of it is almost impossible to imagine. What part of the 1980 story stands out to you the most? Let us know in the comments. 57 people lost their lives. Some, like Johnston, were scientists. Others were loggers, campers, photographers, and homeowners who had either misjudged the danger or refused to leave. The economic toll reached $1. $1 billion, over $3.5 billion in today's currency. And the mountain itself was broken. The elegant cone was gone. In its place was a gaping, mile-wide, horseshoe-shaped crater. The summit was lowered by 1,314 feet. A landscape of vibrant green forest had become a gray, lunar desert of ash and pumice. It was a scene of primordial destruction. A reminder that the ground beneath our feet is not static. It is active, and it is indifferent. After 1980, the volcano rumbled for years. A new lava dome began to grow inside the crater, but by the late 1980s, a fragile quiet had returned. The last dome-building eruption ended in January of 2008. For more than 16 years, the mountain was largely silent, healing, being reclaimed by pioneer species. Until the shaking started again. The 350 earthquakes detected between February and June of 2024 are nothing like the violent tremors that preceded the 1980 blast. More than 95% of them were below a magnitude 1.0. The largest, on May 31st, 2024, was a magnitude 2.0. These are called microquakes. They are completely imperceptible to a human standing on the crater rim. For a seismologist, however, they are deafeningly loud. They tell a specific story, the story of magma on the move. To understand what is happening now, you have to understand that a volcano like Mount St. Helens isn't a mountain with a big cauldron of lava sitting underneath it. That image is a myth. The reality is far more complex. It's a plumbing system. Deep in the earth, about 16 miles below the surface, conditions are right for rock to melt into magma. This magma isn't static. It's buoyant. It wants to rise. It migrates upward through a complex network of cracks and conduits, a vast system of subterranean pipes feeding the volcano from below. Eventually, this rising magma accumulates in a shallower reservoir. At Mount St. Helens, this primary storage area sits somewhere between 2.5 and 6 miles beneath the crater. The recent earthquake swarm had a median depth of 3.5 miles below sea level, placing it right in that critical zone. The earthquakes are not the magma itself moving. They are the sound of the rock around it breaking. As fresh magma pushes into the system, it increases the pressure. It forces its way into tiny cracks, stressing the surrounding crust until it snaps. Each snap releases a small burst of energy, a microquake. An entire swarm of these quakes tells scientists that the system is being re-pressurized. The volcano is breathing in, its subterranean lungs slowly filling. Dr. Seth Moran, the current acting scientist in charge of the USGS Cascades Volcano Observatory, emphasizes that this is a normal part of the life cycle of an active volcano. It's what they do between eruptions. He said before, during a nearly identical recharge cycle 10 years ago, that this process is the volcano getting ready again. The key words are getting ready. It could be years. It could be decades. But the process has begun. This is where the ghost of 1980 informs the science of today. Before that eruption, the monitoring of volcanoes was a far less precise science. Today, because of what happened at St. Helens, the mountain is one of the most heavily wired, intensely monitored volcanoes on planet Earth. The Cascades Volcano Observatory, or CVO, based in Vancouver, Washington, watches it with a network of instruments that would have seemed like science fiction in 1980. They have an array of hypersensitive seismometers that can pinpoint the location and depth of a quake the size of a hand grenade exploding deep underground. They have GPS stations studded across the volcano's flanks, capable of detecting changes in ground elevation no larger than the width of a human hair. And that GPS data tells the most important part of the current story. Despite the magma recharge happening miles below, the surface of the volcano is not moving. It is not bulging. It is not swelling outward like it did in 1980. This is the critical difference between then and now. The cryptodome that signaled the impending failure isn't there. For an eruption to be imminent, scientists would expect to see two things happen in concert: a dramatic increase in the intensity and frequency of earthquakes, and measurable ground deformation as magma forces its way to the surface. Right now, we only have one of those signals: the quiet one. If you find this level of scientific detail valuable, hit the like button. It tells us you want more deep dives like this. And if you have family or friends in the Pacific Northwest, share this video. The real story matters far more than the rumors. The recharge process itself is not new. The CVO has records of longer, more intense earthquake swarms that occurred in the late 80s and through the 90s. One from 1988 to 1992. Another in 1995, a large one from 1997 to 1999. None of them directly led to an eruption. They were all just part of the same slow-motion process of the volcano refueling itself after the massive expenditure of energy in 1980. So the recharge of 2024, while the most significant seismic activity since the last eruption ended in 2008, fits a known pattern. It is a sign of life, a vital sign. But it is not a death knell. The problem is, in the age of the internet, nuance dies quickly, and fear sells. In April of 2026, a story began to spread like wildfire across YouTube and social media. The headlines were apocalyptic. Mount St. Helens is splitting. Scientists confirm 9 million foot failure point. Videos published by clickbait channels showed dramatic graphics of the mountain cracking in half, accompanied by breathless narration about an imminent, world-ending explosion. The claim was a complete and utter fabrication. A hoax. The term 9 million foot failure point is geologically meaningless. It's a string of words designed to sound technical and terrifying, but it corresponds to no known scientific measurement or phenomenon. 9 million feet is over 1,700 miles. That's the distance from Seattle to Chicago. The idea of a failure point that deep within the earth is not just wrong, it's nonsensical. The USGS was forced to issue clarifications, patiently explaining to a panicked public that no, the mountain is not splitting, there is no surface fracturing, there is no failure point, there is no cryptodome swelling on its flank. The science showed a slow, deep recharge. The internet sold a Hollywood disaster movie. This is the new danger. The eruption of misinformation. In 1980, the threat was physical. You could see the bulge. You could feel the ground shake. Today, the threat is digital. A viral video, algorithmically amplified, can create more widespread panic than a dozen steam vents. It preys on a fundamental misunderstanding of how these natural systems work. People hear the word magma and earthquake, and they immediately flash back to the gray, hellish images of May 18th, 1980. I know, I'm asking again. But look, we spend weeks digging into the actual USGS data, so you don't have to fall for the 9 million foot failure point nonsense. A surprising number of you still haven't subscribed. If that's worth something to you, hitting that button is the single best way to support this kind of independent work. The reality, as always, is less cinematic but infinitely more fascinating. The volcano is not a ticking time bomb with a predictable fuse. It is a living system with a rhythm and a cadence that operates on a geologic timescale, not a human one. The 2024 recharge is a data point in a story that began thousands of years ago and will continue for thousands of years after we are gone. The official USGS statement from June 2024 put it in the driest, most reassuring terms possible. Short-term increases in earthquake rates are common at Mount St. Helens and are considered part of background seismicity. Their weekly update from just last week, on July 3rd, 2026, confirmed it again. The volcano is at alert level normal. Aviation color code green. There is no emergency. There is only a process. A slow, methodical, relentless reawakening that we are now privileged, and perhaps cursed, to be able to watch with unprecedented clarity. So what does the future hold? What happens when the recharging stops and the eruptive phase begins? Because it will begin. The USGS is clear on that point. The only questions are when and how. An eruption in the 21st century would look very different from the one in 1980, not because the volcano has changed, but because we have. The population of the Pacific Northwest has exploded. The Portland, Oregon metropolitan area, just 50 miles south of the volcano, is home to over 2.5 million people. The Seattle metro area to the north has over 4 million. These cities are well within the range of significant ashfall from a major eruption. In 1980, the ashfall crippled cities hundreds of miles away. It shorted out electrical transformers, clogged air filters in cars, and shut down airports. A similar or larger eruption today would paralyze air travel across North America. It would threaten the power grid. It would have economic consequences that would make the $1.1 billion price tag of the 1980 eruption seem small by comparison. The greatest direct threat, however, isn't from the sky, it's from the ground. The next eruption may not be a lateral blast. It could be a more traditional, dome-building eruption, like the one from 2004 to 2008. Or it could involve pyroclastic flows, fast-moving avalanches of hot gas and volcanic debris. But the most insidious threat, and the one that can travel the farthest, is water, or more accurately, water mixed with ash and rock. A lahar. Mount St. Helens crater is now home to a massive, growing glacier. It's the youngest glacier on Earth, formed in the shadow of the new lava dome. If an eruption melts that ice rapidly, it would mix with the loose rock and ash on the volcano's flanks to create a volcanic mudflow, a lahar, with the consistency of wet concrete, moving at highway speeds. These lahars can travel for dozens of miles down river valleys, burying everything in their path. The towns of Castle Rock, Kelso, and Longview, all built along the Cowlitz and Toutle River valleys, live in the shadow of this exact threat. This is why the monitoring is so relentless. The legacy of 1980 was not just destruction, it was knowledge. The catastrophe turned Mount St. Helens into the world's greatest natural laboratory for volcanology. The lessons learned there helped scientists predict the 1991 eruption of Mount Pinatubo in the Philippines, saving thousands of lives. The system of acoustic flow monitors now installed in the river valleys around St. Helens is a direct result of that knowledge. They are designed to hear the ground rumbling vibration of an approaching lahar, triggering automated warnings that could give communities downstream precious minutes to evacuate. The 110,000 acres of land around the mountain, designated as the Mount St. Helens National Volcanic Monument in 1982, were set aside not just as a memorial, but as a classroom. It is a place to study rebirth, to watch how life returns to a sterilized landscape. But it is also a place to study the hazard that remains. The mountain is not what it was. The symmetrical cone is gone forever, a permanent scar on the horizon. But the engine that built it, the deep magmatic system that fueled its growth and its violence, is still there. It is intact, and it is slowly refilling. Each of the 350 tiny silent earthquakes in 2024 was a whisper from that engine. A reminder that the beautiful, quiet mountain dominating the Washington skyline is a temporary state. It's an intermission. The volcano we see today is not the final version. It's just the version that exists right now, in our tiny slice of geologic time. Future generations will see a different mountain. It might be taller, rebuilt by slow dome building eruptions. Or it might be gone entirely, obliterated by a blast that dwarfs 1980. We don't know. The scientists at the CIVO don't know. All they can do is listen. They listen to the silence. They listen to the whispers of rock breaking 4 miles underground. They watch for a millimeter of swelling on the crater floor. They wait for the pattern to change from a slow, steady recharge to the frantic, shallow swarm that signals magma is no longer just filling the chamber. It's on its way out. The mountain is